Hi, thank you. So I'm Jason. I'm currently at Sandbox AQ on the research team at the Quantum Security Group. So with that in mind, I'm going to talk about work that I haven't done at Sandbox at all. I'll be talking about the work I did at my time at the University of Waterloo with my advisor, Douglas Stebila. So what am I going to talk about today? Well, first I'm going to give you a schwack of background to make sure we're all on the same page. So I'll start off by talking about what is DNS, what security problems does it have, how are these problems addressed, and then finally, are these solutions to those problems future-proofed? The spoiler is, since I'm standing up here with a slide deck, the answer is probably no, but we'll get into that later. Then I'll actually get into what we did and what we believe to be the solution moving forward to get PQC in DNSSEC. So first off, what is DNS? In order to understand that, you must first understand that computers don't like words and sentences and phrases, they like numbers. And on the internet, we use a string of numbers called IP addresses to address packets around. The problem with that is if I told you, hey, check out my really cool website at 93.184.216.34, I'd probably have very low traffic and no one would care. So we had to come up with a reason to translate something that is memorable, say example.com, a very amazing website, and then map it to something that computers understand. And that's where the domain name system, or DNS, comes from. So what actually happens is if I want to go to example.com, I query this opaque box, the domain name system, ask what the IP address is. You then get the IP address, and then you start talking to the servers of example.com. But let's actually take a look inside this opaque box. So DNS is a distributed database, more or less, broken up into these nodes that we call zones. Each zone is responsible for a certain level of information of the lookup. And this is really nice because as long as the zone above you knows that you exist, you can just get added to the DNS system and just kind of keep going and going and going. So to kind of make it a bit more concrete about what a DNS query looks like, let's use the example. Since I'm a little biased, we'll look up uwaterloo.ca. You would first ask the root name zone at the very top there, what is the IP address of uwaterloo.ca? The root zone will say, I have no idea, but the .ca zone might know. You then go and ask, hey, .ca zone, what is the IP address of uwaterloo.ca? The .ca zone will say, I don't know, but the uwaterloo.ca zone might know. And then you'll go ask uwaterloo.ca, and assuming that there is a valid IP address in there, it will then respond, this is the IP address. Or if what you're looking for doesn't exist, it will say it doesn't exist. This is what a really simple zone looks like. The big takeaway is it's a bunch of key value pairs. So you get a label. They're all the same here, example.com. And then you have types. So the quad A record at the top is an IPv6 address. The single A record is an IPv4, and then we have two records that say these are the name servers responsible for this zone. The last thing you need to know about DNS infrastructure is clients themselves very rarely actually query DNS and the name servers. They will usually contact a DNS resolver, usually run by an ISP or Google or Cloudflare or what have you, and then that server will go and do the lookup. This allows us to use caching to improve performance and also take off load from these name servers. However, this is a crypto conference, so we need to talk about cryptography, and DNS as stock DNS, is susceptible to monkey-in-the-middle attacks. So there's nothing to stop me for when I request the IP address for the Canadian bank CIBC.com for the evil middle box to replace it with some nefarious IP address. And then all of a sudden I'm contacting fake CIBC.com. I lose all my money and I can't make my car payment on the new car I bought this last week. So not ideal. And it's a little worse than this, right? Because clients contact DNS resolvers, and those are and they use caching. So if your cache on the resolver gets compromised and poisoned, then a bunch of clients can go to the wrong place, not just one. Not great. So thankfully, this has been thought about, and the brilliant minds at the IETF thought of the Domain Name System Security Extensions, or DNSSEC, And the high-level idea is we'll add digital signatures to DNS. So we introduce a few new records. So we have 2 keys. We have a zone signing key, which is responsible for actually signing all the records in the zone. And then we have a key signing key, which signs the zone signing key. And we do this because it's a little bit of a pain to construct our chain of trust. So you would make your key signing key very, very strong, whatever your policy of that actually means. And then you would roll over your zone signing key more often and re-sign your zone using that. The other thing worth mentioning is that you won't sign individual resource records themselves. You will sign sets of resource records. So resource records with the same label and same type. You can have several different values and several different resource records of the same label and type. So you sign all of them and generate signatures for all of them. So again, let's make this a little more concrete in our example. It's now horrifically base64 infested and very complicated, but I'll walk us through it. So first we have our first RR set for the IPv4 address and its signature. Then this kind of displays that we're signing sets rather than specific resource records. We have our second RR set with the 2 NS records and its signature. Then we have the zone signing key and its signature, which is generated by the key signing key. And you might be thinking, well, where's the signature for the key signing key? We'll get to that. So it's pretty similar to any other PKI system. We essentially need to get a chain of trust and a trust anchor, and we have this thing known as delegate signers. And that's kind of in place of certificates if we were talking about TLS. So the idea is a delegate signer will take the hash of the key signing key, and you will store that in the zone above you. Unless you're in a root, then there's no zone above you. And you will install that if you're talking about the root, you will install that DS record on any machine that wants to use DNSSEC. You would then query the root zone. You would get the keys. You'd verify that the keys make sense using your trust anchor, and then using the key signing key to verify the zone signing key. And then when you go and query .com of where do I go next, you also find out this is a delegate signer for the zone you're going to. Okay, so post-quantum crypto in DNS. So PQC ideally is just a drop-in replacement, right? Well, unfortunately for us, it's not quite that simple, or maybe fortunately because we got a paper out of it. But we have to keep our messages below 1,232 bytes. And the reason for this is because DNS primarily uses UDP as a protocol, and we want to avoid UDP fragmentation as much as possible. And that's because it's quite fragile. Middle boxes don't particularly like it, so we can't. UDP is not reliable, but fragmented UDP is even more not reliable. So we want to avoid that. The good thing is we do have a fallback, and that is if a message is too large, it will get marked as truncated. When the resolver gets the truncated response, you should fall back to TCP. But that's quite expensive, right? Because then you've wasted a trip to find out that it's too big. Then you have to set up a TCP connection, and then you can start your query again. That's quite expensive. And then a non-trivial amount of names or resolvers fail to fall back to TCP, so not great. How about PQC? So drop-in replacement, right? So dilithium 2, we don't have a hope of even fitting a single thing. If we ignore signature size for a second, Sphinx Plus looks amazing. We can send keys all day long, but then signatures are a problem. Falcon, at first glance, looks quite good. We can fit one of each in a single DNS message. Amazing. However, it's quite common that you have to send, say, 2 DNS keys or public keys, or you need to send several signatures. Sometimes they're a mixture of both. Well, we're over that threshold, so sadly, not ideal. So the question becomes, how do we send large PQC signed messages? Why don't we move the fragile fragmentation from UDP up to the DNS level? So as far as UDP is concerned, no idea about fragmentation. These are just DNS messages. So let's think of a couple ideas. First, if we have a large DNS message, let's just break it up into several DNS messages, insert the resource records into the various messages we need, and we'll just send them to the resolver. With this idea, you would need to advertise as a resolver that you actually support this. Otherwise, you would just get all these extra messages and you have no idea what to do with them. And it also doesn't solve the problem of what if a resource record is way too large to fit inside of a 1232 byte requirement. We don't have a notion of chopping them up. And then finally, these pesky things known as middle boxes, which follows RFCs to the T. I'm joking, they don't usually, may end up dropping these extra DNS messages that are sent because they could see, oh, a client has made a request to DNS and it is just expecting a single UDP-based DNS response. So this unfortunately won't work. Now let's just take the large message as a giant byte string, and we'll just, every time we hit that threshold, we'll make a whole new UDP packet, shove the rest of the byte string in there, and we'll just blindly send them to the resolver. Well, with this idea, how do we handle out-of-order delivery? UDP does not guarantee packet order. You still have the same problem of middle boxes might only expect a single DNS response. And then what if the resolver does not support this fragmentation method? You'd either need to advertise that you support it, or you're going to get all these UDP packets after the first one. Maybe you close your UDP socket, and then you'll receive the others, and then you'll spam a bunch of destination unreachable messages, which makes debugging horrible. And debugging in networking things is already horrible, so let's not make it any worse. So we have an idea. We call it ARF, or a resource record fragmentation mechanism. Whether I came up with the name when I was particularly missing my dogs back home is out of the scope of this talk, but let's get into it. So at a high level, ARF is a DNS level fragmentation mechanism designed with backwards compatibility in mind. So rather than chopping up and creating several or rather than chopping up DNS messages, we will look at the resource records themselves that are causing the problem and break them up. Resolvers will also explicitly request fragments that it's missing or needs, and this will mean that you won't have to advertise that you support ARF, and it will also prevent denial of service amplification to a certain extent, as well as ICMP flooding. And we do not waste a round trip compared to falling back to TCP. And then we can also abuse parallelism to reduce the overall pain of transmitting these larger messages. So you're probably seeing this, and there's a bunch of fields, and what do they mean? It's quite confusing, but the big takeaway you should get from here is a resource record is mapped onto the generic, or a resource record fragment rather, is mapped onto the generic format, so that it's backwards compatible. If a resolver does not support this thing, it manages to actually read this, this RR frag. It won't go out of bounds or anything like that. And then when you're using an RR frag, you can use them in two ways. When it's contained inside a response, it will contain a bunch of metadata about the resource record that can't fit inside the message. And it may or may not contain data. And we'll get into that in an example in a second. And then when it's contained in a query, it contains the metadata that what it's looking for, and it basically says, hey, I want this block of this large resource record contained in the response you'll send me. So let's do a quick example. So say there's a resolver asking for some A record, and then a name server constructs this large DNS message with a large signature in red there, and it realizes, hey, this thing is way too big. It's going to exceed the 1232 byte limit. It then changes the message into a truncated message, and then replaces in place the large signature with the resource record fragment. Now, the reason we mark it as truncated is for backwards compatibility reasons. So if a resolver receives this message, has no idea what ARF is, it will see it's truncated, and then it should just fall back to TCP. Then the resolver, after receiving that truncated message, and in this case we do support ARF, will see, hey, this is the fragment I've received. Here's the information about the resource record that was fragmented. And then in this example, we'll place 2 parallel requests for the missing fragments it needs. You then again, the resolver or the name server will see this, create 2 more messages that are again truncated with the requested data. You reassemble the thing, and then you get the large DNS message. Finally, in terms of DNSSEC, when do you actually validate this thing? Well, you wait until you can reassemble the whole message, then you perform the DNS, the signature validation, and then assuming that all passes, you're safe to insert it into your resolver cache. So is this thing any good? How did we evaluate it? We used Open Quantum Safe's LibOQS and their OpenSSL fork and added a support for Falcon 512, Dilithium 2, and Sphinx 1 plus 128S, the SHA-256 variation, to ISC's DNS bind 9 software. We then implemented a daemon which will run in front of bind 9. So as far as bind 9 is concerned, it doesn't know what ARF is, it doesn't care, it just responds to messages as if it was normal. And then the daemon will intercept these messages and perform ARF transparently. And then in order to set up our network, we use Docker and NetM to set various network conditions. What do the experiments actually look like? So we performed 1,000 queries for distinct A records for each of the 3 algorithms, and we made sure that the queries were distinct so that caching didn't get involved. We wanted to get a fair comparison without caching. And then we tested over a variety of network conditions, whether it's the perfect dream scenario of no delay and unlimited bandwidth, maybe one day, I don't know, and then, or all the way to 100 milliseconds of delay and 50 megabytes per second of bandwidth. We also evaluated how it performed if we artificially restricted the message size, and we did this to see what happens if you fragment a lot or a little. And then we compare our results against DNS as specified today with TCP fallback. And we used maximum parallelization, so no restrictions, make as many requests as you want at the same time. But we imagine that operators would probably want a rate limit to some degree, so we also do the other extreme and look at you can only make a single request at a time, the sequential case. So in interest to not make your eyes glaze over with a million numbers that may or may not make sense at first glance, I'm only going to cherry pick one set of results here. More or less all of the different scenarios told the same story, but if you don't believe me, go check out the paper. But if we start off by looking at standard DNS with TCP fallback, we can find that PQC is roughly twice as slow as classical crypto, which is a little painful. When we use parallelized ARF, however, we kind of half the pain. So I call that a little bit of a win. And then in fact, in the Falcon 512 case, sequential ARF also roughly halves the pain. So that's quite nice. If we look at what happens when you have to fragment a lot, perhaps nobody's surprised, the parallelized version where you can make as many requests as you want at a single time, they all perform roughly the same. But then the more you have to fragment and the larger the messages, the large messages you have to send are, it roughly scales in the sequential case as you would expect. More requests means slower. How much data did we use? Well, I was pleasantly surprised when I originally ran these numbers that in light to moderate cases, we used less data than falling back to TCP. And this will be because of things like the wasted round trip. We don't waste any round trips, so you save bytes there. We don't have to establish a connection like TCP does, so you save some bytes there. And then TCP with its ACK will end up utilizing some bandwidth as well. So as long as you don't have to fragment a lot, you end up saving some data. But There is more overhead per request for ARF, so if you do enough requests, enough fragmentation, eventually we do end up using more data to transmit the same thing. What about security concerns? So the good news is, since we explicitly request every single fragment, it doesn't make denial of service, amplified denial of service, any worse than DNSSEC today. And also, if a resource record fragment is modified in transit and you're using DNSSEC, which you all should, the validation will fail. So that's all good. So that doesn't make the security model any worse. Then we also mandate that these fragments should never be cached, so there won't be an issue with cache poisoning. However, as spec'd, ARF is susceptible to memory exhaustion attacks. So what if in that initial response that gives you all this metadata about the resource record, someone changes the size of the resource record that's being fragmented to, say, 64 kilobytes, the resolver receives it and then allocates 64 kilobytes for something that it doesn't need to, and you just keep doing that over and over again, then you get killed and everyone's very, very sad. So future work, we need to address the memory exhaustion attacks. Of course, because that's kind of a big deal. We did design ARF with backwards compatibility in mind, but ultimately we tested on a synthetic network, so we need to test on the real live internet and see if it is actually backwards compatible. We also didn't address the concern of an unreliable network, so we'd probably need a timeout of some sort, but more study needs to be done there. And then also, does the idea of request-based fragmentation work for any other protocols? We believe so. There's a paper on the archive called Turbo TLS. Please take a look at it. Let us know if you think it's good, bad, okay. Would love some feedback on it. So to conclude, ARF is a lightweight, performant, and easy to implement modification to the DNS protocol. It enables transmission of these larger post-quantum signatures and keys in DNSSEC. It also removes the need for TCP fallback in order to send these large messages. We're not saying get rid of TCP fallback entirely, but if you don't have to set up a connection, why should you? It performs roughly 20% better than when having to fall back to TCP when you're using parallelized ARF. And in fact, in certain situations, even the sequential ARF performs better. And then also in cases of light to moderate fragmentation, we use less data to transmit the same thing compared to TCP. So that's my spiel. Thank you very much for listening, and I'm happy to answer any questions you may have.
Do you have any plans to bring this to the IETF to propose this being built into DNSSEC as a change or an extension?
So yeah, I would like to, definitely. It still needs some more work though, in my opinion, before we write a draft and get people's opinion on it. I've talked to someone from VeriSign that seemed to think it was an okay idea at least and needs some evaluation. They might be doing some work on it as well, but that's still very early. So short answer is yes, I would really like that. Long answer is too soon.
Thank you.
Yep.
Hi, I'm really no expert in the domain, so it's really likely that the question has no sense at all. But when we use DNS over HTTP, is the connection only between the client and the resolver, and then the resolver uses the normal DNS with a name server? Yeah, exactly. So DNS over TLS or HTTPS are both client to resolver. And then you use standard DNS from resolver to name servers. Okay, and is there any point in adding some DTLS layer on top of UDP in order for the security to rely on directly the DTLS layer instead of the DNS protocol?
That's a great question. I don't see why we couldn't do that. There has been people suggesting doing, so DNS over QUIC has been standardized between client resolver, but there are people that are asking, well, do we do it between resolver and name server? And the root zone operators came out and were kind of against it. They made a letter and said, we don't want to do this. So I'm not sure how receptive they would be to DTLS, but you never know. It's a cool idea for sure.
Thank you.
Thank you.
Okay, can we thank our speaker?